Hello, Professor Henniger here again with my associate Maverick. He's going to be my diligent associate for this set of activities. And what we're going to do is the actual physical data collection, observation, and to draw conclusions for our activity. As you can recall from earlier in the video, this is our miniaturized solar panel, more for our activity size. You can't really generate too much electricity with this because of its size. It's connected through these power cables, one red and one black, and that takes the electrons that are bumped by the visible light traveling through our wires to this little motor. And at this motor, we have a wheel connected, and I've attached an impromptu flag so that we can see its rotation depending on our experiments. Now for our first part of activity, I've got this worksheet describing the outline of photovoltaic activities and different steps, and I have here my actual worksheet, which I've kind of to start to fill in, but we're going to replicate the experiment so that you can do this in your own locations. So my associate Maverick here, we have an incandescent light bulb. I can turn this off, and you can see it inside our light fixture here. Okay, that's going to replicate the sun. Maverick here is going to replicate our solar panel assembly, and we're going to use it to kind of estimate and discover the effect of the visible light coming from our light bulb hitting the solar panel, bumping electrons essentially, collecting those electrons and turning it into electricity. So what we're going to do first here is turn on our light bulb. That's going to represent our sun. And on our worksheet, as you'll see when you do this on your own, there's some information here, one being, are we inside or outside? So we checked off inside. We did the size of the solar panel. That'll tell us how much electricity it can produce in a later activity. And the type of light source, in this case, it's an incandescent light bulb. You could try an LED light bulb or a compact fluorescent light bulb to see what kind of results you get with those sources of visible light as well. We're just going to focus on the incandescent for the inside part of our experiment today. Now, for this part of the assignment, we're going to start at a distance farthest away, which, when you're talking about visible light, the energy dissipates over a distance. So we're going to see here, if we keep our distance at about, say, 1 foot, about 12 inches away, Maverick's going to hold it nice and taut there, and how close we are perpendicular to the sun, our light source. So we want to hold it just about where he is to gain the most direct incoming visible light to see if we produce any electricity. Before you do this, you can certainly work with your classmates to see what kind of conclusions you might or come to, or hypotheses. Will this turn the motor? Will it not? And it also depends on the type of wattage light bulb you use. Right now we're using a 40-watt light bulb, and so we'll see if we can generate enough visible light to turn the motor. So Maverick's going to hold it there and see if we get it. I may have to prod it along because I kind of have an inclination that it won't be enough, but that's the joy of science, is discovering it on your own. And as he holds it there, thank you, Maverick. Let's see if we get any induced rotation. Nope, doesn't look like it. So for this light bulb, at a distance of 12 inches away, we're getting 0 revolutions per minute. It's not too surprising, but you'll be able to confirm this on your own when you start at this distance. Well, as Maverick and I tried at a distance of 12 inches away from the light source, and we got 0 revolutions, meaning that there was not enough energy, visible light, to cause a bump of electrons, we're going to move it in a little bit closer, and we're going to say maybe 9 inches, and we'll put it right about there, making sure that we stay perpendicular in this part of the experiment, which we are. Let me just double check that here. We got 9 inches, and we're about, oh yeah, we're nice and perpendicular there. That's a great angle. And so we're going to see here, again, filling out our worksheet as we go along, how far we are. We're going to put 9 inches here, and let's see if we can get any rotations. Again, I may have to cheat a little bit here to induce rotation because I suspect that it won't be close enough to generate electricity with this type of light bulb at this distance. But that's also the joy of learning. you can do this as well in your own activity. So 3, 2, 1. Maverick, let's see if we get any luck. How's that? Nope. Nope. So for a light bulb of 40 watts, 9 inches, and perpendicular to the incoming energy, we still get 0 rotations. It shouldn't be surprising, but what you can try are different wattage light bulbs. With stronger wattage, you may actually get some rotation here, but for the purpose of this experiment, we're at 0 still. All right, well, Maverick and I are here trying again to get our sustainable energy project working. And of course, it's different in the real world with the sun being so intense as it is at 93 million miles away. We're trying to replicate how far away does the solar panel have to be from the light source to turn the motor to show us that it's going to revolve. So far, we've done at a distance of 12 inches, we've done 9 inches, and now we're going to try 6. So Maverick's going to move it in right about there, okay? And we're going to double check to make sure that we're perpendicular. So you hold your protractor up to the distance, and we're just about at 90 degrees, okay? And again, based on earlier observations, I'm skeptical if we're going to get enough power, and we're going to see. Now, if it did start to spin, we would let it spin for a second or two, and then we would time it for 30 seconds, multiplying that number by 2 to see how much revolutions we get, and that will tell us the intensity. So let's try, Maverick. What do you say?
Let's go.
All right. 3, 2, 1. Nope. I sense a little bit, but not enough to do it on its own. So as you can see, even at 6 inches away, it's still not intense enough to produce an electrical current and bumping those electrons to spin our wheel of science. Let's see what 3 inches does, shall we? All right, we're nearly at the surface of our light source, and we're going to move this solar panel all the way in, buttressing it up against the light bulb, trying to gain as much energy as we can from this light source. And again, this is just for representation. So basically, if we just move this back for a second, we could say we're about, 2 inches away, maybe 1.5 inches away when we're right here. And hopefully, finally, as you fill out your table, okay, we're still at incandescent at 9, 6, and now at 3. We're still at a 2 by 3 inch panel, so we fill out our worksheet appropriately. And we're still inside, using a 40 watt incandescent light bulb. So now we want to see if we can finally generate and reveal how a solar panel works. And not only reveal, but show the importance of location, distance, orientation, angle, and available light source, sunny versus shady, to see what kind of power we can generate. So hopefully, science will do me right now and see if we can get this rotating. Would you look at that? The wheel is spinning at a very high velocity. Now, for this project, at 3 inches, I would attempt to count how many rotations it's doing over 30 seconds. And you could probably, with a couple of your classmates, come up with a number, but I'm going to put in very, very fast. Now, the goal is to try and count, but if you can count that fast for 30 seconds, you have a certain different ability than I do for this experiment. But you can clearly see we need to be very close to the light source to get enough electricity to rotate the wheel and to spin our little fan bladed attachment. So it does work. And with this, you will be able to draw up some conclusions about not only distance away, size of the solar panel, and then also the amount of energy it produces in this very, very simple experiment. Okay, here we are. Our wheel is spinning fervently and with quite a lot of gusto even. And if you can, you might even be able to hear it spinning a little bit in the audio representation. Okay, you can kind of hear it vibrating its stand and vibrating the table, so it's really moving. But we're going to try something interesting here, something a little different. And so what Maverick's going to do is slowly pull the cell away, and we're going to see how that affects the rotation. I'll tell him when to pause, and we can see and finally measure how far away it is as to when the wheel stops spinning. All right, you with me, Maverick, here?
With you.
All right, good. So at the count of 3, Maverick's going to slowly pull it away, and I'll stop him, and we'll see what the results are and the effect, actually. 3, 2, 1, pull it away just a little bit here, Maverick. Okay. Still going pretty strong. You can see it rotating. Now wait there. Now you can almost see, we've only pulled it away about an inch or two, and you can see, hopefully, how much slower the wheel is turning. So distance from the light source has a lot to do with it. Ironically, we are 93 million miles away from the sun on the Earth here as we rotate around the sun every year. We do 1 revolution. And that distance is still strong enough to produce an immense power of electricity that we haven't really fully tapped to yet on planet Earth. So as Maverick holds it here, we're going to continue now to pull it away from the light source, and let's see what kind of effects that causes. Okay, keep bringing. Okay, hold it there. Let's see if we can get an idea how far away we are. We can say we're about 3.5 inches from the light source, and you can see how dramatically slower the wheel is now spinning. And so this has a real big impact on not only the size of solar panels we need for our rooftops of our warehouses and buildings and solar farms, but also the distance and angle. Now, if Maverick holds it here and tilts the solar panel, let's see if that changes the speed of the wheel as well. So he's going to hold it at the same distance away and tilt it. Keep going, keep going. Whoa, keep it right there, Maverick. That's perfect. You can see, now tilt it back up again. Let's see if I can get it going. You can see when he tilts it back that it slows down. Right there is perfect. So the angle of the solar cell to the light source has a lot to do with it. So some of you or your friends that have solar cells and panels on your roof, the angle of your roof tells a lot about how much energy you can actually produce. So not only distance, but the angle of the solar panel relative to the light source is a big impact on the speed and electricity produced. Now, Maverick's going to bring it back straight up, okay? And then he's going to bring it back till it finally stops spinning. Slowing down. Now hold it there. See if we can hold it. Okay, we're still generating electricity. That's really good. Really good. But you can see how slow it's going now. And bring it back just a little bit farther, Maverick. Right there. And you can see it just basically stops. So move it in a pinch. Let's see if we can get it restarted. Okay, good. That's perfect right there. You can certainly see how much slower only a short distance is made in the electricity it produces, and therefore the speed of the wheel. Incredible, cool science just from light and moving electrons. All right, well, we've relocated outdoors. It's a pretty nice day today. We have a thin veil of clouds overhead, but as you can see by my squinting and Maverick squinting, that it's still very bright for late spring, actually. And so let's see if this solar panel is actually working and what kind of energy is it producing even with this cloud cover today. So I'm going to power it up by plugging it in. Okay, and I might have to give it, there we go. And as you can see that it's rotating pretty vigorously in a very strong motion. I can feel its little vibrations on my hands as I hold it here. And we're not even sure if we're perfectly aligned to produce the electricity that we aim for. So Maverick here is going to slowly tilt it towards the camera, and we'll be able to see by the rotation how it changes. So as he does this, I want to talk about alignment and angle to the sun. And so solar panel companies do an assessment of a location. They'll be able to measure what angle is best between the high sun of summer and the low sun of winter. What's the best mix for either times of those years? So right now, if we hold it there, Maverick, you can see pretty clearly how much it's slowed down, because the light energy is coming in at a very sharp angle and not as straight on, perpendicular to the surface. So angle does play an important role in producing solar electricity. Okay, Maverick and I, we've determined that sometimes too high of an angle can be a bad thing. We don't have much electricity being produced. So just for interest's sake, let's bring it back down, see how that changes our electrical production. Oh, you can see the wheel starting to really speed up. We come to the optimum angle, maybe for the day and for the season. And just to see what happens, I'm pretty sure you can presume and deduce what will happen. But if we keep going backwards, away from the incoming solar radiation, well, there you have it. It's pretty clear. Let me just move this out of the way. As you tilt away, solar panels become ineffective, which is not surprising because the sunlight doesn't bend and hit the panel. We have to have the panel properly aligned, which is critical, but also sometimes a compromise between the angle of the sun, what kind of surface it's going on to, the angle of the roof or the incline, and then also we have to think seasonally, because if you remember, the sun's not always high up in the sky like it is now. During the winter months, it's lower on the horizon and will produce different amounts of electricity. All right, as we close out this demonstration, which has been pretty mind-blowing if you ask me, a star from 93 million miles away sends its light, bumps off electrons in this solar cell, which is and also a mini solar panel rather, and the electricity here moves onto those metallic wires, transferred as electricity to this direct current motor, which spins our wheel. So a last question would be, well, what if there is either shade that grows over the site in time, or say there's dust, or say for some reason one of the sections of the solar panel stops working? How could that impact your electrical generation? So Maverick here is going to slowly tease this solar panel, this miniature one, and we're going to see the effect of reducing the flow of electricity cell by cell by cell by cell. And let's see what we get by the time, when it does stop. Okay, so once you do the first corner there, Maverick, and slowly creep over it, we're just using a piece of paper, fold it over, and oh, look at that, hold it right there. Notice the dramatic decrease of electricity production. Pull it away real quick. You can see it speed up again. How important each cell of this whole solar panel is needed to produce electrical generation. Try that again slowly. We see if we can catch it slowing down there, Maverick. Okay, he's over 1/8 of this entire cell, and you can see how dramatically slower the wheel is actually spinning. That is very, very cool science right there. Now, just to really explore this topic, Maverick's going to move it again over this second little cell, and let's see if that really impacts. Okay, it grows, and there we go. So if debris or if an electrical connection breaks, and these are very sensitive, they're very tough, but they're very sensitive too, gets in any way interrupts the flow of electrons, electricity stops flowing. So pull them back off, Maverick, and let's try something one last time. So we bring it back up to full power, even with a cloudy day. Now, just to see what happens, let's cover these two cells here first and see what happens. So we change the orientation of the paper, and I'll slide it over there gently. Okay, you can see with me how it's slow. Oh, look at that. So again, anytime you interrupt the flow of electrons with a shady material, you can see how the electrical production dramatically drops off. So you say to yourself, Maverick, why do I care? Why do I care? What is so cool about this? Well, this is very cool because any interruption affects how much electricity we produce. Okay, in the Earth we have an atmosphere. These will get washed off. We could cut branches away or put them in very open spaces, trees that are far, far away from shading us. But think about the importance here, say for the Mars rovers and the Mars instruments that are actually there right now. There's a situation where dust from the Martian landscape can land and be deposited on the solar panel. Well, that's pretty critical because I don't see you or I going to Mars with a watering can or a hose to clean off these cells. So we are always developing technologies to make these more efficient. So in terms of the Mars example, they have to wait for strong Martian winds to blow the light dust off of the solar panel so that it can continue its scientific exploration on an entirely other planet. That's the far-reaching impacts that renewable energy, particularly through solar panels, can have and will have in your lifetime. From myself, Professor Henniger, and my silent great assistant Maverick, we want to thank you for watching this demonstration today. I hope you can enjoy solar electricity as much as I have and exploring the awesomeness of renewable energy. Thanks for watching.